Imagine waking up one day to discover that your home, the ground beneath your feet, the water in your veins, the very planet you've called yours, your entire life, might not have originally belonged to your sun at all. Not because of some freak cosmic accident, not because of a random chaotic collision billions of years ago, but because your star, the one that rises every single morning with quiet, clockwork reliability, the one that poets have worshipped and farmers have depended on for 1,000 years, the one that feels so permanent and so ours, is a thief, a patient, methodical, ancient thief that has been hiding its crime for 4.5 billion years. And the evidence? It has been drifting in the cold, lightless dark at the very edge of our solar system the entire time, waiting silently for us to notice. That is not a metaphor. That is not science fiction dressed up in dramatic language to make a YouTube video feel more exciting. That is the emerging scientific consensus that is quietly but systematically reshaping how astronomers understand our place in the galaxy, what our solar system actually is, and whether the word ors even means what we think it means when applied to the worlds drifting around our sun. For generations, we told ourselves a clean and satisfying origin story. The sun formed from a collapsing cloud of gas and dust. A spinning disk of material surrounded it. Planets condensed from that disk. Earth assembled itself from local ingredients. Comets delivered water to the young oceans. Life crawled out of the sea billions of years later. Everything in this solar system started here, grew here, and belongs here. Our solar system, our stuff, our home, it is a tidy story. It is also, at minimum, seriously incomplete. Because at the frozen, lightless edges of our solar system, in a region so remote that light itself takes more than a day to travel from the sun to reach it, objects are drifting in orbits that make absolutely no sense. Orbits that cannot be explained by Neptune. Orbits that cannot be explained by any planet we currently know about. Orbits so stretched, so tilted, so geometrically bizarre that the most rational explanation astronomers have been able to arrive at after exhausting every other option is that these objects did not form here. They formed somewhere else, around a different star, in a different solar system entirely. And our sun, during a chaotic and violent youth, we are only now beginning to reconstruct, reached out across the void and took them. This is the story of the greatest heist in the history of our cosmic neighborhood. It involves a nursery of thousands of newborn stars packed so tightly together they were practically elbowing each other. It involves billions of stolen objects now drifting silently in our outer solar system. It involves a shadowy, unseen planet potentially larger than Earth that may be a refugee from a completely different stellar family. And it involves the quietly staggering possibility that some of the water currently flowing through your body may have begun its 4 billion year journey orbiting an entirely different sun. The more astronomers look at the edges of our solar system, the harder it becomes to see this place as the closed, private, self-contained neighborhood we always assumed it was. And once you understand what they've found out there in the dark, what the orbits are telling us, what the math implies, what the simulations keep confirming, you will never look at the night sky quite the same way again. The nursery, where the crime was committed. To understand how the theft happened, you have to go back before Earth existed. Before our sun existed as the calm, reliable, middle-aged star we recognize today. You have to go back roughly 4.5 billion years to the very beginning of our solar system's story, and to a beginning that was far more crowded, far more chaotic, and far more violent than our tidy textbook version ever acknowledged. Our sun did not form alone, stars almost never do. They form in clusters, vast, collapsing clouds of gas and dust where thousands of stars condense simultaneously in the same region of space, packed together in a blazing, gravitationally tangled community that astronomers call a stellar nursery. The name makes it sound peaceful. It wasn't. Imagine a city where every building is being constructed at the same time. The streets are jammed shoulder to shoulder with competing forces, and everything around you is radiating heat and light and gravitational influence in every direction. That begins to approximate the environment in which our sun spent its first 100 million years of existence. Multiple young stars would have been visible simultaneously from any point in the cluster. There was no real darkness, just a glowing, seething crowd of stellar infants, each generating their own gravity, each tugging on their neighbors, each disturbing the fragile outer edges of every nearby star's newly forming planetary system. And in that environment, in that extraordinary, luminous, gravitationally chaotic nursery, things did not stay where they belonged. When two young stars drifted past each other at close range, within a fraction of a light year, a planet sitting in a wide and loosely held orbit at the outer edge of one star's gravitational grip suddenly found itself caught between two competing forces. For tightly bound inner planets, this was no danger. They were held too firmly to be pulled away. But for planets and icy bodies in wide, fragile outer orbits, the situation was genuinely precarious. If the geometry was right, and in a dense birth cluster, the geometry was right with unsettling frequency. The passing star's gravity won. The object was pulled away, not violently, not dramatically, just gradually, inevitably, across thousands of years of slow gravitational persuasion, until a world that used to orbit one star found itself falling toward a new one instead. It ended up in an elongated, stretched orbit, swooping relatively close to its new star at the nearest point, swinging far out into the cold dark before slowly falling back again. It was, in the most literal astronomical sense, a theft, conducted in silence across millions of years, with no witnesses. This cosmic shoplifting lasted for roughly 100 million years, the lifespan of the birth cluster, before the sibling stars gradually dispersed into the wider galaxy. Astronomers have actually confirmed some of these siblings. HD 1 Treaty 2826, sitting about 110 light-years away, has been verified as a solar sibling, born in the same stellar cradle as our sun. There are almost certainly thousands more spread across the Milky Way, each carrying their own mixture of native and stolen material, each a quiet participant in the same vast, slow exchange. The question that drives this entire investigation is what our sun came away with. What did it take? How much of it is still out there? And can we find it? Sedna, the object that broke the mortal. In November 2003, three astronomers, Mike Brown of Caltech, Chad Trujillo, and David Rabinowitz, discovered something that immediately stopped them cold. A reddish world, roughly 1,000 kilometers across, drifting through a region of the outer solar system where nothing of its kind was supposed to be. They named it Sedna after the Inuit goddess of the sea, a figure who, in legend, was banished to the frozen depths of the ocean by her own father. The name turned out to be more fitting than they initially realized, because Sedna had been banished too, cast into an orbit so remote, so elongated, so fundamentally unlike anything else in the known solar system that it immediately broke every existing model for how the outer solar system is structured. Here is why Sedna is so important. Most objects in the outer solar system carry what astronomers informally describe as Neptune's fingerprint. Neptune is the gravitational authority of the outer solar system, the traffic cop that redirects anything drifting too close, throwing it into a looping, elongated orbit that eventually passes near Neptune again. The Kuiper Belt works this way, comets work this way. You can examine almost any outer solar system object and trace its strange path back to a gravitational encounter with Neptune at some point in its history. Sedna doesn't have that fingerprint. Its closest approach to the Sun sits at about 76 times the Earth-Sun distance, so far beyond Neptune's reach that Neptune could not, under any physically credible model, have influenced it in the slightest. The distance is simply too great, the gravitational influence too weak. Neptune cannot have put Sedna where it is. The numbers don't work, and they don't work by an enormous margin. At its farthest point, Sedna swings out to nearly 1,000 times the Earth-Sun distance before beginning its long, slow 11,000-year journey back inward. The last time Sedna occupied this position in its orbit, human civilization was in its absolute earliest stages. The pyramids hadn't been imagined. Writing didn't exist. And yet Sedna was already old. Already billions of years into an orbit it never should have been in. Since its discovery, astronomers have found a small but growing collection of similar objects. 2012 VP-113, nicknamed Biden, Leliakuhonua, nicknamed the Goblin, a cluster of detached trans-Neptunian objects, each sharing the same impossible characteristic. Orbits too remote and too strange to have been produced by any planet we know. Their tilts are wrong. Their distances are wrong. Their very existence is, under the standard model of solar system formation, wrong. So what put them there? Two explanations have emerged, and both of them are extraordinary. Planet 9. The Shepherd we haven't caught yet. In 2016, Mike Brown teamed up with his colleague Konstantin Batygin and published a paper that immediately commanded serious attention. Their argument was this: the detached objects are not randomly distributed across the sky. Their orbital paths cluster. They point as a group in roughly the same direction, as if something massive has been herding them into alignment through slow, repeated gravitational nudges over millions of years. The probability of that alignment being a random coincidence, by their calculation, is less than 1 in 10,000. The simplest explanation is a planet, a large undiscovered world, somewhere between 5 and 10 times the mass of Earth, orbiting at distances hundreds of times beyond Neptune, in a stretched, elongated path that brings it periodically close enough to exert a consistent gravitational influence on the detached population. They named it Planet 9, and the name has stuck even as the debate around it has intensified. Planet 9 has not yet been directly detected, but searches are actively ongoing, and the tools available for finding it are improving rapidly. The Vera C. Rubin Observatory, which has recently begun its decade-long survey of the southern sky, is currently the strongest instrument we have for this purpose. If Planet 9 is orbiting anywhere within the survey's range, Rubin has a real and serious chance of catching it. But here is where the story twists in a direction that changes everything. Because Planet 9, if it exists, immediately creates a deeper and more urgent question. Where did it come from? It is far too distant from the Sun to have formed in place. The disk of gas and dust that built our solar system's planets thinned out and dissipated long before reaching the distances Planet 9 is theorized to occupy. A world of that mass simply cannot have condensed from the solar disk at those distances. The physics rule it out. So, either Planet 9 formed much closer to the Sun and was gravitationally ejected outward during the turbulent early history of the solar system, or it didn't form in our solar system at all. In 2018, Harvard astrophysicists Amir Siraj and Avi Loeb ran the numbers on that second possibility. They modeled the probability of our Sun capturing a free-floating planet during its time in the birth cluster, and their answer was significant. The probability is non-trivial. Not high but calculable, scientifically serious, genuinely possible. If Planet 9 is real, and if that capture scenario holds, then orbiting somewhere beyond Neptune is an entire world. Larger than Earth, with its own deep geology, its own core chemistry, its own ancient history that does not belong here. A planet that formed around a different star, in a completely different solar system, that was gravitationally stripped from its original parent during the chaos of the stellar nursery and permanently absorbed into ours. A refugee world, cold, dark, massive, silent, carrying in its rocks and ice the molecular memory of a birthplace that our sun never knew. How gravity culminates the crime on the mechanics of stellar theft are, once you understand them, almost elegant. When two young stars drift past each other at close range in a birth cluster, a planet in a wide outer orbit around the first star finds itself caught between two competing gravitational fields. For tightly bound inner planets, the passing star poses no real threat. They're held too firmly by their own sun. But planets in wide, loosely bound outer orbits are vulnerable. The passing star's gravity can compete with the home star's gravity for control of these objects, and if the geometry is even approximately right, the visitor wins. The planet is pulled away, not in a collision, not in a dramatic separation, but in a slow gravitational drift across thousands of years, until it is no longer orbiting its original star and has begun falling toward a new one. It settles into a stretched, elongated orbit, close to the new star at its nearest approach, then swinging far out into the cold dark before slowly returning. That orbit, elongated, eccentric, tilted relative to the disk, is the signature left behind by every object captured this way. Sedna's orbit matches that signature. Planet Nine's theorized orbit matches it even more dramatically. Computer simulations by Susanna Falzner at the Max Planck Institute have quantified how often this happens. In a typical birth cluster like the one our sun came from, somewhere between 1 and a few percent of all small, icy bodies in a star's outer system may be captured rather than native. That sounds small. But the Oort cloud, the vast spherical shell surrounding our solar system's outermost reaches, is estimated to contain somewhere between 1 trillion and several trillion individual objects. 1% of even the lower bound of that estimate is 10 billion. 10 billion objects, potentially of foreign origin, drifting silently through our solar system right now, indistinguishable at first glance from objects that formed here, carrying the chemical fingerprints of stellar birthplaces that our sun never shared, locked into their molecular structure across 4.5 billion years of cold, quiet orbit. Reading the evidence, orbits and chemistry. How do you prove an object was captured rather than born here? The evidence comes in two forms, orbital and chemical, and both are pointing in the same direction. Objects that formed in the flat, spinning disk around the young sun orbit roughly in the same plane as the planets, because the disk itself was flat. That is what native solar system membership looks like in orbital terms, alignment with the plane. An object arriving from another star at a random incoming angle will have a tilted orbit. Sometimes slightly, sometimes dramatically, sometimes almost perpendicular to everything else. Now examine the detached population. Sedna's orbit is tilted 12 degrees from the plane of the planets. The Goblin sits at 24 degrees. Other extreme trans-Neptunian objects show inclinations of 30, 40, 50 degrees. Some orbit at nearly right angles to the rest of the solar system, almost completely perpendicular, as if they arrived from a completely different direction entirely, which, according to the capture theory, is exactly what happened. You don't produce those tilts from a flat disk. You produce them from objects that came in from directions having nothing to do with that disk. The chemical evidence is potentially even more decisive, though harder to collect. Every star imprints a unique chemical recipe onto the objects that condense in its disk, a specific mix of elements and isotopes shaped by the star's age, mass, and galactic location. Two stars born in different environments will produce objects with subtly different chemical fingerprints. If we could analyze the surface composition of a captured object in sufficient detail, we might find isotope ratios that fall outside the range of what our solar system's disk could have produced. A molecular passport stamped with a different stellar address. We don't yet have that resolution for most candidates. They are too small, too dim, too remote. But the James Webb Space Telescope and the extremely large telescope, currently under construction in Chile, are rapidly changing what is measurable. Within the next decade, detailed surface composition analysis of outer solar system objects will move from impossible to routine. If even one of these detached objects returns a chemical profile that doesn't match our sun, the case is closed. The theft is proven. Interstellar visitors caught in the act. Here is where the story stops being purely about ancient history and becomes something we have actually witnessed in real time. In October 2017, astronomers detected something moving through the inner solar system at a speed and on a trajectory that proved, unambiguously, it had not originated here. It came in from interstellar space, looped around the sun, and departed on a path it would follow forever. The first confirmed interstellar object ever observed passing through our solar system. They named it ʻOumuamua, Hawaiian for a scout or messenger from the distant past. ʻOumuamua was strange in multiple ways. Its shape appeared elongated, possibly cigar-like, possibly disc-like. As it departed, it accelerated slightly more than solar radiation pressure alone should have produced, leading to significant scientific debate. The leading explanation is outgassing of volatile ices as it warmed near the sun, providing a gentle additional thrust. But the full picture of what ʻOumuamua actually was has never been entirely resolved. 2 years later, in 2019, amateur astronomer Gennady Borisov spotted a comet traveling on a hyperbolic path, curving around the sun and then heading outward in a direction no solar system object could take. Borisov was interstellar, a comet from another star, making one brief solar encounter before continuing its journey between the stars forever. 2 confirmed interstellar visitors in 2 years, after centuries of observation yielding 0. That timing is not coincidental. It reflects improvements in our detection technology, reaching a threshold where such objects can finally be spotted. And the implications are significant. Astronomers now estimate that at any given moment, several thousand interstellar objects of meaningful size are somewhere within our solar system. The vast majority are too small and too dark to detect. Most are also moving too fast to be captured. They'll pass through and vanish. But a small fraction will arrive at the right speed and angle, receive the right gravitational nudge from Jupiter or Saturn, and be permanently absorbed. They'll settle into tilted, eccentric orbits in the outer solar system and remain there, effectively forever. We've already found one compelling candidate. A small object called 2015 BZ509 orbits in the opposite direction of every planet in the solar system. Every planet, every object that formed from the spinning solar disk, orbits counterclockwise when viewed from above the North Pole. 2015 BZ509 goes clockwise. That retrograde orbit is essentially impossible to produce from a disk that rotated in one direction. Its discoverers concluded it was almost certainly captured from another star. It has been hiding in Jupiter's gravitational shadow, going the wrong way around the sun for potentially billions of years. Almost no one noticed. What this means for use. the personal dimension. Here is where the story transcends astronomy and becomes genuinely personal. We have always understood Earth as fundamentally local. Our origin is our own. The sun formed, the planets formed, the comets that bombarded the young Earth all came from the same cloud, the same disk, the same family. The water in the oceans arrived from our comets. The organic molecules that seeded the prebiotic chemistry leading to life were products of our solar system's chemistry. We have always assumed, entirely the children of our sun. But if a significant fraction of the outer solar system was captured from other stars, and the math increasingly suggests it was, then the comets that struck the early Earth were not all native. During the late heavy bombardment roughly 4 billion years ago, the young Earth was relentlessly struck by objects from the outer solar system. Those impacts are believed to have delivered a substantial portion of Earth's water and the organic compounds that eventually led to life. If some of those impacting objects were captured, if some originated not in our sun's disk but in the outer reaches of a different, long-dead star, then some portion of Earth's oceans came from somewhere else. Some of the molecular building blocks of the first living organisms may have formed around a foreign sun, been frozen into a comet, stolen by ours, and eventually crashed into our alien planet during those ancient bombardments. The water in your body, in some small but scientifically real percentage, may not have originated in this solar system. It may have been borrowed billions of years ago from a star that has since exhausted its fuel and faded into darkness. That is not poetic license. That is what the orbital math applied to the bombardment record of the early Earth actually implies. And the exchange runs in both directions. Our sun lost objects too. Worlds originally formed in our young solar system were ejected by gravitational chaos among the giant planets or stripped away during close stellar encounters in the birth cluster. Some are now rogue planets, cold, dark, sunless, drifting between the stars. Some have been captured by other stellar systems. Somewhere in the Milky Way, there may be an object quietly orbiting a foreign star in a tilted, eccentric path, born in our solar system, living in someone else's. A piece of our family, unknowingly hosted by strangers, just as we are unknowingly hosting pieces of theirs. Astronomers estimate that the number of free-floating rogue planets in the Milky Way may rival or exceed the total number of stars. The galaxy's inventory of worlds is not neatly sorted by stellar origin. It is constantly, thoroughly, irreversibly shuffled. Worlds traded back and forth over billions of years of gravitational interaction. Origins blurred almost beyond recovery. Boundaries between ores and theors dissolved by time and gravity until they are essentially meaningless. The hunt. What's coming next? The extraordinary thing about this moment in history is that we are better equipped to pursue these answers than ever before, and the instruments capable of delivering them are either already operational or coming online within years. The Vera C. Rubin Observatory has launched its decade-long legacy survey of space and time, a comprehensive, methodical scan of the entire visible southern sky, revisiting the same regions every few nights, flagging anything that moves or changes. Rubin's combination of aperture, camera size, and automated detection software makes it essentially a planetary dragnet engineered precisely for this kind of search. Astronomers expect it to discover tens of thousands of new trans-Neptunian objects, many of them in the detached, tilted, suspicious orbits that point toward foreign origins. And if Planet 9 is anywhere within the survey's reach, Rubin has a genuine shot at finding it within the survey's 10-year window. The James Webb Space Telescope, operating in the infrared, where cold and distant objects are most visible, has already begun expanding what's measurable in the outer solar system. Surface composition analysis that was previously impossible for small, distant objects is now becoming feasible. The extremely large telescope, under construction in Chile's Atacama Desert, will provide ground-based resolution that pushes past anything currently imaginable, enough to begin extracting detailed chemical profiles from outer solar system objects that are currently too dim and too remote to study meaningfully. And beyond the telescopes, some scientists are beginning to seriously land something more ambitious. A dedicated space probe sent not to fly past one of these detached objects, but to actually rendezvous with one, to match its orbit and travel alongside it, to study its surface composition directly at close range over an extended period of time, to touch, in the instrumental sense, the surface of a world that may have last received sunlight from a completely different star. Such a mission would be extraordinarily challenging. Travel times to the relevant distances are measured in decades, not months. A probe dispatched today might take 50 years to arrive. The scientists who designed it would likely never see the data it returns. But it would answer the question in a way no telescope ever could, with ground truth, with direct chemistry, with the definitive test of whether what we're looking at is native or for foreign. Closing. The thief and its silence step back from the individual details. Look at the whole picture. Our solar system, the place we have always imagined as our stable, bounded, private cosmic home, is not what we thought it was. It is not a closed garden. It is not a sealed neighborhood with a clear inventory of original residents. It is a way station. A slow, wide clearing in the galactic road where objects drift in and drift out across timescales that dwarf all of recorded human history, where the line between ours and theirs has been blurring continuously for 4.5 billion years. Some of what we think of as ours arrived from somewhere else, and some of what was once ours has already left, flung outward by gravitational encounters, now drifting between the stars or quietly orbiting a foreign sun on the other side of the Milky Way. Sedna is the emblem of all of this, sitting out there in the dark, 76 times farther from the sun than Earth, completing one 11,000-year orbit in slow, patient silence, in an ellipse that no planet we know of could have produced. Sedna is a world in captivity, a world that belongs to a solar system that no longer exists. Whatever star it originally orbited is almost certainly gone now, burned through its fuel, scattered, silent. Whatever planets once shared that original system are dispersed or captured elsewhere or lost. Sedna kept moving, our sun caught it. And it has been here ever since, bound to an orbit forced upon it by a star that was not its own, moving through the long, patient rhythm of something that belongs nowhere. And if Planet 9 is out there, cold, dark, massive, silent, in an elongated orbit 1,000 times beyond Earth's distance from the sun, then Sedna's story is written at planetary scale. A whole world, chemically foreign, holding in its core and ice the molecular memory of a birthplace that our sun never shared, waiting in darkness for the instruments capable of finally finding it. When we find it, and I believe we will, within the next decade or two, as Rubin and Webb and the next generation of observatories sweep the outer sky, we will not simply be adding a ninth planet to the textbooks. We will be meeting a refugee, opening a window onto a stellar family that no longer exists, a solar system that scattered or died or simply moved on, leaving one of its children behind in our custody. And the sun, that ancient, patient, brilliant thief, will keep its face still, its light warm and steady, its expression utterly unchanged. Rising every morning over a solar system that is part native and part borrowed, part ours and part someone else's, holding the secret it has held for 4.5 billion years. As if nothing happened at all,